have a little look here. So we get to move into the last little part of differential calculus. This is pretty cool stuff. We're gonna talk about optimization. So the whole point here is we want to either minimize or maximize some quantity. And when you, well, let's take a look at this example, and I'm just gonna do an intro today. We'll look at one or two examples, but I want you to think about this two ways. I want you to think about it in terms of graphs, for one thing. That's very helpful. You know, if you can think about what the graph of the quantity that we're trying to minimize or maximize would look like. Just not specifically, but just what the setup would look like. You know, what would go on the horizontal axis and what would go on the vertical axis. And then think about this in terms of the curve sketching stuff that we've been doing, okay? So what are we doing here? We've got this manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in the figure here. What dimensions will produce a box with maximum volume? Okay, so what is the quantity that we're trying to maximize in this case? 108 is important. It's volume, isn't it? Right? And they give us some information about this box. Okay. Well, you know what? I'm going to hand you. I'm going to pause this for a minute. In this case, the quantity we want to maximize is volume, right? Find maximum volume. So how do we go about doing this? Well, just like we did with related rates problems, one thing we're going to want to do is we want to be able to come up with a picture if possible and define all the variables. Well, that's already been done for us in this case. X represents the width of the square base and H represents the height, right? Once we've done that, really the first thing we want to do is we want to come up with we want to write a function for the quantity that is trying to be maximized in this case, and that's called the primary equation, right? What is it that we're trying to maximize or minimize? What's volume, right? So what is the volume of this box? X squared times H, okay. So V equals X squared times H, okay. So we're trying to, if we think about this in terms of a graph, what's the quantity that's going to go on the vertical axis? It's V, yeah, it's V, right? So we're going to graph something that's going to look kind of like this. We're going to have V on that axis, right? We got to figure out what's going to go on this axis. Now this is going to look similar to a lot of stuff that we did last section, right? Where instead of V, maybe we'd have something like F, and we had X down there. Okay, and if we're trying to find where the volume is maximized, isn't that like trying to find a maximum of a function, right? So where do maxima occur for a function? Say it again. Okay, they have to be at critical numbers, don't they? Where the first derivative is either undefined or equal to 0. Some of those will pan out, some of them won't. The ones that pass the test, what are they going to end up looking like? What are the kinds of places on the curve, on the graph of the curve, where the maxima can occur? Could be negative concavity. And what do we call that thing if it looks something like, let's say we had peak or a relative maximum, right? Could also occur potentially at an endpoint, right? This is, because really what we're trying to do here is we're trying to find, you know, based on whatever the domain of this function is going to be, you know, based on the description, we just want to know where is the volume the biggest. Okay, so it could be at an endpoint or it could be at a maximum, right, a relative maximum. So we've got to go find those places. Now, what's the problem with this function right here? You got two independent variables, right? What's that going to look like? Now, we're not ready for that yet, but if we were to graph a function with two independent variables, we'd have to add another axis coming out of the board. Maybe we call this one x and this one h, and then instead of having just a single curve, we're going to have a manifold. We're going to end up having a surface that's looks like a like a map, right? Like we're looking down on terrain. And so peaks and valleys. Now we're not going to do that in here. This class really should be called calculus of a single variable. In fact, that's what, if you have the thinner version of the textbook, that's what it says. Calculus of a single variable, because we're not going to deal with calculus of surfaces, right? It's not hard to do, and that's something you'll do in college. When you get to the next class in calculus, you'll just you'll sort of take what we've learned and run with it a little bit. But it's not a big deal. It's really not a huge extension to talk about finding, instead of just a peak on a two-dimensional curve, you're going to find the peak on a three-dimensional curve, right? Just the very top of the mountain. But we don't want to do that. We're not ready to do that yet. So what must we need to do to this function? Yeah, we've got to come up with some other equation of constraint, some other equation that's going to relate x and h so I can substitute. Okay? So because we have two variables, we're going to need some secondary equation. And the secondary equation has to relate the two independent variables. Now, a lot of times, I'm not going to write that way. A lot of times, well, not a lot of times, always. The secondary equation has to provide some kind of a limit, right? Because if there were no limits on this, it'd be pretty simple to do. How big would you make your box in order to maximize the volume if there were no limits? Yeah, I'd make mine infinitely wide and infinitely tall. That's not a very useful question, is it? Right? So a lot of times the secondary equation is called the equation of constraint. What's a constraint? Like a limit, something that's limiting, the scale of this box in this case, right? So the equation of constraint is always going to involve a number then, or at least a constant, right? Well, what's the number up here that constrains this? Surface area, yeah, 108 square inches. That's what constrains this to not be infinitely big, right? So then the equation of constraint, or our secondary equation, is the surface area equation for this box. So what's that going to be? Surface area is equal to what for this thing?
X squared plus.
Okay, so
HX
x squared, that's
4HX.
that's the base, right?
Plus 4hx.
Plus 4 times the area of one of the sides. So there's four lateral sides on this thing, right? So 4 times x h, and what's that constrained to equal? 108. There you go. Okay, so there's our secondary equation. All right, so now what? Now what are we going to do? We want to reduce the number of independent variables to 2. It's always the same way. We're going to make a substitution. Okay, but we have to be strategic about this, right? We don't want to, it's theoretically we could solve for either one of those variables, x or h. So which one makes way more sense in this case? H does. Give me one reason why h makes more sense. Because it's not squared. Okay.
Because there's only
What's another one?
there's only one.
Yeah, look at this. I've got a single h right there that matches the single h right there, right? X would be tough. If I wanted to solve for x, I'd have to solve this quadratic equation and get multiple cases and try all those. I mean, it'd be tough, right? clearly we want to solve for h in this case. So if I isolate h, what do I get? Okay, I'm gonna subtract the x squared to this side and divide both sides by 4x. Okay, so let's put a box around it because that's my substitution equation, right? And then now I can take this substitution equation and I can make my substitution. Okay, so then what do we end up with? If we make our substitution, we now get volume equals x squared times h, right? And what's h? Well, here's our h, so all this stuff. Okay, and we can simplify that, right? But what can we do to make that a little easier? Distribute, sure. So if we distribute the x squared, and we could even do this, couldn't we? We could even cancel, we could say, okay, I've got an x squared over an x, so those cancel, right? Then I could just distribute the x and get 108x minus x cubed all over 4. Right? So there's my volume equation. Now, whoops, now I'm going to write this as, v of x, because this is, now we've got volume of the box as a function of x, which, remember, is the width of the base, right? So v of x equals this. And we could pull the 1/4 out front if we want to. We could, split it into terms if we want to. Let's do that. Break it into terms. What is this? 27x minus x cubed over 4. And look what we can do now. That looks good, right? That looks like the stuff we dealt with in 3.5 and 3.6, right? Where we had a function of x. This might as well be f of x. And we're trying to find the peaks and valleys. But remember, this is not purely mathematical. This is a physical, geometrical situation here, right? So we need to find the domain of the function, okay? Of the primary function. Now that we've got it limited down to a single variable, x, what are the values of x that we could use? What values of x would make sense in our domain? Greater than 0. 0 wouldn't really make sense, would it? If it were 0, then h would have to be infinitely high, and that's not going to work well, right? Okay. In fact, if x were 0, the volume would be 0, and that's not. We're not trying to find a minimum. We're trying to find a maximum, right? So one thing we could do is we could say, and you can include it or not. It doesn't matter really either way. What if I do include it? It's not going to be a point that's going to work, but I could include it in my, because there's no mathematical reason not to, right? Could be in my domain, be a bad choice. What about the upper limit? How are you going to find the upper limit?
Solve for x in the surface area equation.
We could consider the surface area equation, right? What's going to happen if the volume, if the surface area is fixed, it's 108. I've got just quantitatively, qualitatively, not quantitatively, pretend this hand is giving the, big or small value of x. This hand's going to measure the relative size of h. What happens if this one gets bigger? If x gets bigger, h has to get smaller, doesn't it? Right? Because the surface area is fixed, right? So would you agree that when x is at its minimum, h is at its maximum, right? That make sense? Okay, so x really couldn't even be 0, could it, as far as h is concerned? Because if I split this apart, I'm gonna get 27 over x minus x over 4, right? If I broke this into pieces, my equation for h, right? And so if x went to 0, h would go to infinity, right? Everybody see that? Right? Because that would make the bottom of this, of one of these fractions 0, would approach 0 while the top stayed the same. Okay, so let's flip it around. As x goes to its maximum, h would go to its minimum, right? Well, what would the minimum value that h could at least approach be? Imagine the box. It'd be 0, wouldn't it, right? As h got smaller, the base is going to get bigger, right? So if we went back up, this is oftentimes a good way to think about this. If we went back up to this equation right here, and we set h equal to 0, what value of x would cause that? When is a fraction equal to 0? When the top is 0, good. So we could say h equals 0 when 108 minus x squared equals 0. So what would the solutions of that equation look like? X equals, if I solve that, add the x to this side, square root both sides, plus or minus square root of 108, right? What is square root of 108? 26, so what is that? 9 times 12, so 36 times 3, right? So it'd be 6 radical 3. Does minus make sense in this case?
No.
No, x can't be negative, right? You can't have a negative distance. And so the upper limit for x would be 6 radical 3, wouldn't it? Right? Because that's when h is 0. So then everybody agree that's our domain? And whether you include 0 or not, it's really it's up to you. I mean, it's not gonna, you can if you want, but you don't have to. In this case, there's no mathematical reason you can't, but you know it's not gonna work anyway. Different people will choose to do that differently. But somewhere in there is gonna be our maximum, okay? That is just a calculus problem, right? We've gotten this down to the point now where we can just do our table and get an answer, right? And usually these end up being pretty optimization problems. Honestly, they wouldn't necessarily have to be this way, but the ones that we look at typically are going to be geometric or they're going to be economic. And usually they're really simple. You've done much harder ones already, like in 3.6, where you had to look at really complicated functions and find all the relative extrema and inflection points. We don't really care about inflection points in this problem. All we want are extrema. So then this is a pretty easy one to do. We would just make our table. What do we need for our table? We've got our function. What else do we need? First derivative. So what's first derivative? (27)
Minus 3/4x squared.
minus, okay, I'm going to bring the 3 down, so minus 3/4 x squared. And while we're at it, it's so easy to do, it's a polynomial. What's the second derivative? Negative 3/2 x, yeah. Okay, so let's grab all that stuff.
But we don't even need the second derivative for this one, do we?
You don't need it, but the second derivative test is so easy to use. If it's really easy to do, you should use the second derivative test. Okay, so then we'll just make our table here, right? So we got x, v, prime, v double prime, our domain went from 0 up to 6 times the square root of 3. Well, let's analyze our first derivative. Where is the first derivative going to equal 0? V prime equals 0 when what? X squared equals what? I get,
6.
yeah, I'm gonna get 3/4 x squared equals 27. So x squared equals 36. So what's x equal? Plus or minus 6, but the only one that's gonna be in our domain is just gonna be 6, right? So somewhere in there we get 6, which is a 0 of the first derivative. What's the sign of the second derivative for any positive value of x? Negative. So what is this? Yeah. It's going to be a maximum, isn't it? Right? And if there's only one relative maximum on a function that's smooth, right? It's continuous. This is just a polynomial, right? So it's going to be smooth everywhere. So what does that tell you? Just using logic, you don't check the endpoints, do you? Right? What would the volume be at the endpoints? Without even really thinking about it.
0.
It'd be 0, wouldn't it? Right? You're gonna have 0 there and 0 there, because if you have either no width or no height, you don't have a volume, do you? Right? Okay, this would be if all the area of the box were just the base. But you don't even have to think about that. You just know that based on the shape of this curve, if it doesn't have any asymptotes, right, it's nothing weird, it's continuous, and if the only place where it's got a maximum is right there, it can't turn back up again, right? Because in order to turn back up, it would need a minimum, and there aren't any. There's only one critical number, right? So this is just going to be something like that. And there's our peak. Right? So what did the question even ask? Now we go back and one of the dimensions. Okay, so we know that x is 6. How would we find h? Go back to the substitution equation that we put a box around, right? If I plug in 6, I'm going to get 108 minus 36 is what? 72 divided by 24 is 3, right? So we get h equals 3. So the dimensions would just be 6 by 6 by 3, whatever the units are, inches, right? Okay. Base would be a 6 by 6 base, and the height would be 3. Okay. Is that what you expected? I would have asked you probably what would people have said the shape was going to be for this.
You're probably just gonna think about that for like a second and come up with.
It would have been hard to come up with this one. Most people would typically say it would be, you'd want it to be a cube shaped, right? Because a cube is, like if you wanted to maximize volume for a given surface area where the surfaces were all closed, you'd make it a cube. But what made this different? Yeah, there's no top. Right, there's no top on it, so it changed it. Okay? Does that make sense? So let's kind of backtrack and just take a look at the sheet. Let's think about these steps in the context of what we just did. So step 1, well, we got to get a picture if possible. We got to assign the variables. Right, so in this case, x equals basis width, h equals height to the box, right? You gotta write, you always start off with what are you trying to accomplish, right? We're trying to maximize what? Volume. So you always start off with a primary equation. Sometimes that's all you need, because what if the primary equation right away is a function of only one variable? Then you can skip down to where did we first do our, we can skip down to here, right? We can skip down to the place where here we had volume as a function of a single variable. Maybe we get that right away, but we gotta know what the domain is then, right? That's the next step, we gotta know the domain. If, like we had, there are multiple independent variables, then we have to come up with an equation of constraint, right? We're not gonna go any further than one equation of constraint.
Joshua.
But you could have multiple. You could have, what if we had 3 independent variables? Then we would need more than one secondary equation to break all that up into a single equation of one variable, right? We won't do that here this year. This is, as far as we'll go, is 2 independent variables, so we need one equation of constraint, okay? And then the equation of constraint allows us to write it in terms of a single variable. And once we get to there, once we have a function of a single variable, and we figure out what the domain is, then it's a piece of cake. Then it's just a little calculus. Make a table, right? Okay, let's try, how much time we got? We don't have a ton, do we? Let's just set one up at least. How about, we'll start one that we can finish tomorrow. Okay, so there's the question. What are we gonna do? Step 1. We need a primary equation. There isn't really a picture to make of this. It's not a geometric thing, right? Our variables are, looks like X and Y. I mean, if we want to, we could do just a little sketch of this graph, but we don't even need to, right? What does this look like, by the way? 4 minus x squared. It's a parabola. What can you tell me about the parabola? Opens down. Where's the vertex? 0, 4. Yeah, so it'd look, if we were to do a quick sketch, it would just look something like that. And the point 0, 2 is right there, right? Okay, so our primary equation, what is it we're trying to find? Okay, our closest. So let's translate that into a different question. What is the quantity we're trying to minimize or maximize? Distance. Okay, so we need a distance equation. What's that going to be? What's distance? Okay, right. So we've got some point on this curve up here that's going to have, we know that the coordinates of the point that we're trying to find the distance from are 0, 2. In general, the points, just a random point on the curve is going to have what coordinates? Well, we could call it something like x1, y1, right? Okay, so then, once again, what would the distance be between those points? Okay, so we know, you guys remember the distance formula,
Is it
right?
square root of x minus, well, x1 minus x2 squared plus
Okay.
y2? Yeah.
Okay, so yeah, if we call this distance, let's call it s, right? Then we could say that s equals the square root of delta x squared plus delta y squared, right? The difference in the x coordinates. So x1 minus 0, right? Plus y1 minus 2 squared, right? Does that make sense? So S is the thing that represents the distance. Okay.
So it doesn't matter.
Does that make sense?
So, do we really need the x1 squared because of the zeros?
Say it again.
Because, oh,
Yeah, we do, because it's inside, we don't need to put minus 0. Okay, but that's an ugly looking equation, isn't it? What's so ugly about that?
X squared root y1.
The square root, right? We've got a radical in there. Okay, now let's think about this logically here. Are we trying to find the distance?
No, we're just trying to.
No, we're trying to find the coordinates, right? That minimize distance, right? So we're not technically even trying to find distance. So do we have to, well, could we come up with a different function that's easier that would have a minimum at the same place? Well, I mean, we're going to have to take a derivative, right? But that's going to be an ugly derivative. Do we need the square root in there? No, right? S squared, isn't this a better equation? And you don't have to do it this way, this is just kind of a good little trick. S squared would equal x1 squared plus y1 minus 2 quantity squared. Isn't the square of distance going to be a minimum when distance is a minimum? Right?
Yeah.
So let's just call that f. How about it? That's our function that we're going to minimize. Okay? Does that make sense? I mean, we might as well minimize s squared, right? Okay, we'll pick that up tomorrow.